forgot to record.
Yep, thank you. I'm recording now. So if you remember, technically our definition was that the cosine of A would be the x value over the radial value. But that radial value here is B, so we're just taking that radial value, calling it B, multiplying it over. B cosine A is the x, and comparatively or similarly, the y value is B sine A. We used that when we built the angle sum and difference formulas as well for cosine. So we have all of those coordinates there. I want to do a similar type of construction as we did for law of sines. If we drop an altitude down there from angle C and figure out that height, well, we can figure out that height this kind of in a similar way as we did for law of sines. But, well, yeah, anyway. So we're going to find this angle or this side length A based on that height and those coordinates. Well, what do we know about that side A? Well, it's in this big right triangle here. It's in this right triangle. So for that right triangle, Pythagorean theorem should hold. So that A squared should be equal to that height squared, plus this length, which for a minute here I'm going to call L squared. But the nice thing is we know that height. That height is B sine A. That's the y value there. So that height is B sine A, quantity squared. This length here isn't C, but that length is that length C minus the x value there. So C minus that x value of B cosine A squared. So if we simplify this, we'll get a tool. So let's simplify it. A squared equals B squared sine squared A, plus FOIL this out, we'll get C squared minus 2CB cosine A plus B squared cosine squared A. For multiplying that out, square the first twice the product, square the last. A squared equals, we've got B squared sine squared A. I'm going to move these around a little bit, plus B squared cosine squared A minus 2, I'm going to write that as BC, I just like it better. BC times the cosine of A. What is sine squared plus cosine squared? Samuel's throwing up gang signs, I think. Throwing up a 1, but does have that B squared in the way. So if we factor out that B squared, the resulting sine squared A plus cosine squared A, that's going to equal 1 in there. Oh, where'd my C squared go? I lost my C squared. So plus C squared. I'm going through this tool kind of quickly because I want you guys to see where it comes from, but I don't want to get too bogged down in it. So our A squared is equal to B squared plus C squared minus 2BC cosine A. So that result is the simplified form of this tool. And remember, the goal of that tool was to give us an opposite pair, and it gives us an equality between, if we know an angle, it will give us the length of the side opposite. Now, technically, it gives us the square of the length of the side opposite. But square root that, and we'd have A. So this tool down here is what we call the law of cosines. And I really do like to think of it as a tool for constructing that opposite pair. But it is also often thought of as, well, something slightly different. We know if we wanted this other side here, like I'm just going to call it A, we know that we can't use Pythagorean theorem up here. We can't say that that A squared is equal to the 7 squared plus 8 squared. Pythagorean theorem doesn't hold because it's not a right triangle. Well, notice that's the first several terms of this tool. What this tool is essentially an extension of Pythagorean theorem for non-right triangles. It starts with Pythagorean theorem. The sum of the squares of these two sides equal the square of the other side. We're used to seeing the hypotenuse labeled C, but it doesn't matter what it's labeled. So it starts like Pythagorean theorem, but it adds this check, this little modifier for it not being a right triangle. So it's kind of the Pythagorean theorem fixed or extended. If this angle was 90 degrees, then this A would be a hypotenuse. So it would be hypotenuse squared equals the side length squared. And this angle would be the cosine of 90 degrees. The cosine of 90 degrees is 0, and it would zero out this entire check. So this even simplifies to the Pythagorean theorem if the angle you're talking about is a right angle. Fair? So it really is nice to think about it, an extension of Pythagorean theorem, whose goal tends to be build me opposite pairs. So we can figure all this out. A squared is equal to, what, 49 plus 64 minus, what is 8 times 7? 56. So that's 112 times the cosine of 50 degrees. So is that 113? 113 minus 112 cosine of 50 degrees. None of you will fall into the oh so tempting trap of subtracting those, right? You would never do that. It is funny to watch people who, been doing algebra for years and are like, I would never do something like that. Then all of a sudden they're subtracting those because it's so tempting. But let's see, we got what, 113 minus 112 times the cosine of 50. And now I'm in degree mode, so this will come out better. So 41, almost exactly 41. That's nice. So yay, that side length is 41, right? So that side length 41? Seems a little long, but is that okay? Say no. Square root 41. Yeah, careful about that as well. It's really easy to get that value and say, yay, I'm done. Sometimes that value is crazy large, and sometimes it looks like it's not too unreasonable depending on the lengths, but do make sure you do find that square root, and don't forget that it's technically plus or minus, but we're really going to be using the positive one in this case. So what is that, 6 point something? 6 point. Not gonna make me mind it all you. I'll just go with 6. Okay. Sam's going to come to my rescue. 6.4. And 6.4 certainly seems more reasonable up there to scale. Fun? Now, the nice thing is we still need, if we want to fill out the rest of this triangle, we still need these two angles. But we have law of sines that we can use now. Because we generated an opposite pair, we don't need to use the kind of big, clunky law of sines. It's a great tool, but it does tend to be a little bit more computationally heavy. We can go to law of sines, as long as we're careful. Now, we've got two angles here. We've got the blue angle and the green angle. If you can see my colors, hopefully you guys can see the colors. So the question I have for you guys is, which of those should we find first, the green one or the blue one? Or does it matter? So throw out an opinion there. Which one do we want to find first? The blue one, the green one, or it doesn't matter? Sam went with blue. Okay. Nick, doesn't matter. Jay went with green just to be argumentative. Those are the three possible answers. So I am going to argue with two of those answers. Since I'm going to argue some, that means I'm automatically going to argue a little bit with Nick. It does actually matter. It does make a difference. Use blue because of given information. Nicholas, I like that thought, trying to use as much given information as possible. Always a good default, but not where I was going. Let's say, for sake of argument, we went with blue. Either because it's good information, because we like blue. Samuel, I'm not sure why you said blue. You might have just liked blue, or because of the using the given length. We have to use the 6.4 anyway. So really, either one, we'd be using either the given 7 or the given 8. But let's say we started with the blue. Then we would say the sine of that blue angle, I'm just going to arbitrarily call it b over 8, has to be equal to the sine of the 50 degrees in ratio to the 6.4. So take a moment and find that angle B. Move this out of my way a little bit. I want to compare that to finding the green. mean, they should be the same, right? Nick, that was your argument that there's not really any difference there. So, Sam, you said blue, right? So that means you get to tell me, what did you get when you solved for B?
I got 0.9576.
Was that for the length of B, the angle B, or was that your value for the sine of B?
That was the value for. Oh, I see what I did. Okay, that was for sine of B. Okay.
So find angle B. Who else said blue? Back you up. Nicholas, you said blue as well. What did you get for B, Nicholas? No. Samuel, do you want to come to Nicholas's rescue?
I got 73.26.
So that just might be a difference in approximation. So let me ask you, Samuel, how did you get from the number you had before to your 73.26? What did you do?
I sine inverse.
And when we use an inverse function, we get
two numbers. Okay, that's right.
So why are both of you giving me one number? 73 point. I'm going to go with, well, one rounds up, one rounds down. I'm going to go with 73 degrees. Make it easy on myself. Or, what's the other one? Or 107 degrees.
Yep. 107.
Do we know whether that blue angle is acute or obtuse? We don't know. So either one of those could work. Now, because this is a side angle side triangle situation, side angle side, we don't have an ambiguous case. So it's not both. It doesn't break us into two answers or two triangles. One of those numbers works for the triangle we're given, and the other one doesn't. We just don't know which is which. By contrast, the green one, if we solve for C, how many answers are we going to get when we use the sine inverse there? How many answers do we always get when we use a sine inverse? What are they? $56.9 and 123.1. So we still get two answers, but do we know if the green angle is obtuse or acute? Yes. I'm not sure what you mouthed there, Shay, but could you tell us what that was?
I talked to myself a lot, I'm sorry.
That's okay.
Because for C, it has to be in between the 50 and the blue angle because it's the medium length.
Right. This 8 is the largest side length we have. So the angle opposite it is going to be the largest of the angles. The 7 is the medium, so the green is the medium angle. 50 is the, well, 6.4 is the smallest side, so the 50 is the smallest angle. It is impossible to have two obtuse angles in a triangle. So the only one that's possible to be obtuse is that blue. So the blue might be obtuse, it might be acute, we don't know. The green has to be acute because it's not the largest angle in the triangle. You can imagine contradiction. You can imagine if it was obtuse, so it would be 90 degrees plus. Then if the blue has to be the largest angle, it would have to be obtuse and even more. So then the blue would be 90 plus. Already you'd be over 180 degrees. So we don't know which one of these is true. I don't know. But we do know which one of those is true. Does that make sense? So then we could go, okay, angle C has to be 56.9 degrees. And then instead of finding angle B with law of sines, take the 180 minus the 50 minus the 56.9, and we never have to worry about whether it's obtuse or acute. It'll just come out to be whatever it is. There. And what does it come out to? 180 minus 106.9. Well, clearly that's 73 degrees, right? So hey, in this case, the acute was correct. But we didn't know that. It's quite possible that the 107 could have worked. So the moral of this story is don't use law of sines if you can avoid it. Don't use law of sines to find the largest angle because you won't know which one's which. Fair? Use law of sines to find medium or small angles, and then use your other tools to get at the large angle. Now, really, the other choice would have been, well, we found these sets and we don't know which one's which, so we could compare, like those two are too big, those two plus the 50 would be too big, so it's got to be these. So you can find the blue one first and figure it out. But what tends to happen when people find the blue one first is they do what you guys did, which was they only find this one, forget that one, which works sometimes. Fair? So it's a strategy issue. Make sure you're not putting yourself in a position where you have to use law of sines to find a large angle. And remember, we can tell which one's the large angle because it's going to be opposite the large side. As another example, this is actually a fairly common thing to need to do in construction applications. So let's say this side length is 12 this side length is 10, and this side length is, oh, I don't know. Let's go 9. I don't want 9 there. I want, what do I want? How about 18? Remember, diagram not to scale, right? So we're told to make this thing, and for our construction process, it would be really handy for us to know what these angles are. So we want to go find these angles. And we get to choose what order we want to do it in. So what order do you want to do it in? Which one do you want to find first? The blue, the green, or the pink? And Nick, I'm going to go with you this time. It actually doesn't matter which one we start with here. Sort of doesn't matter. So sort of yay. So which one would you like to start with? Blue, green, or pink? You guys get to pick. Green. Okay, start with the green. Now, green is a smart choice because it is the only one that can be obtuse. We will be using law of cosines to find that angle, and law of cosines doesn't give us the ambiguity that sine does. So get the big one out of the way first so we don't use law of sines later to try to find it. So finding the biggest angle first is great. Finding the biggest angle last is great. Don't find the big angle in the middle. So that's a great choice. Nick, it gets it out of the way. We'll be safe. What does the law of cosines tell us? It tells us that that 18 squared has to equal the 12 squared plus the 10 squared minus 2 times 12 times 10 times the cosine of that unknown green angle, which I'm going to call A for arbitrary. Thank you, Shay, for laughing at that. I appreciate when somebody laughs at my jokes. So use that to solve for A. I'll give you a couple of minutes, give you 2 minutes. Solve for A. Some books will actually give you this form as an alternate form of the law of cosines. So if you're trying to use law of cosines to find angles, some people will just go right to that as if it's a different formula. It's just the same formula solved for cosine anyway. So who wants to tell me what they got for A? got an error. Anybody else get an error? You fixed it. Okay. Then what did you get when you fixed it? Are you forgetting something, Shay?
I haven't gotten there yet.
But you used an inverse function, so how many answers are you going to give me? What? What? 109.47 degrees. And this is cosine, so the other answer is down here. Oh, they both say at once. So either negative 109 or something in quadrant 2, so I don't care. How's that? Sorry, in quadrant 3, so I don't care. Can a quadrant 3 angle live in a triangle? No, you can't have an angle over 180 degrees in a triangle. So it's not going to matter. If your original answer was in quadrant 1, okay, that would mean the other answer for cosines in quadrant 4, also something that can't live in a triangle. So while we still get 2 answers because we are using an inverse function, because it's cosine, only one of those angles can ever live in a triangle. So we don't have to worry about what the other one is. It's not that we don't get another one, it's that we don't care. Fair? And frankly, the easiest one to do is just go to 100 and, negative 109.47. Fine. But that can't be in a triangle. Neither can the other one. Fine. You want to do the other one? It's what, 250.53 degrees. I can't live in a triangle either. Fair? So either way, don't care. And notice it did come out obtuse. So if we had tried to find angle A with law of sines, we would have had to have used the obtuse angle. So it's a good thing that Nick had us avoid that and find the green one first. It's the only one that risked being obtuse. If it's obtuse, law of cosines will give us the obtuse value and no risk. So it's a good choice. Also, it now doesn't matter whether we find the blue or the pink one next, because neither of those can be obtuse, because they're not the largest ones. So the rest of the problem is perfectly safe, because you found that big one using law of cosines. So yeah, we got to use law of sines to find the next one, but we know we'll use the acute answer, so safe. So which one do you want to find next, blue or pink, since it doesn't matter? This would be a great question to answer because you know you're going to be right. Pink. All right. Absolutely, Sam. Completely correct. Let's find the blue one instead. No, just kidding. So we want to find that pink one. I'm going to call it B for no reason. So the sine of B in ratio to the 12 has to equal the sine of the 109.47 in ratio to the 18. So B is equal to the sine inverse. It's safe for me to write that because we know it will be the principal sine inverse because it has to be the acute angle. Now, we still technically get two of them, but we automatically disregard the obtuse one because we know B to be acute. And what do we get for B? $38.94 degrees. I know you meant degrees. Now that leaves only the blue one. We could use law of sines again to find the blue one. Heck, we could use law of cosines to find the blue one. We could use law of cosines to find all of these if we wanted to. But that's using, you know, the big hammer for the small nail. In the first one, we have to use law of cosines. Law of cosines can often be a little bit more cranky numbers, so we tend to use that only when we have to. In the second one, we can use law of sines. Law of sines has the ambiguous issue, but we've avoided that by being clever and listening to Nick. But now that we have two angles, the third angle, we can always just get by subtracting from 180. So use the right tool for the right job. And whatever we end up with there. What do we end up with there? 140, 100, so about 30. $31.59. Thank you. So 31.59 degrees. And again, notice the big side length gave us the big angle, 109. The medium side length gave us the medium angle, 38, almost 39 degrees. The small side gave us the small angle, 31 degrees. Has to happen, always true. And surprisingly handy sometimes. Let's see. Oh, that's our time, actually. But we've got a couple of days that we'll be playing with law of sines and law of cosines kind of in tandem with each other, kind of seeing how they play off of each other. I've got some fun examples I want us to look at over the next couple of days. But that's law of cosines. Pythagorean theorem brought a couple thousand years into the future from its original conception. And a nice tool for making those opposite pairs we need. Anything I can do for you guys before you trundle off today? No? Then go forth and trundle. And have a wonderful day. You're very welcome, Chef.